So welcome to the presentation on how to get ready for operations with a clear vision of data needed. And unfortunately, Ursula couldn't present today. So my name is Caroline Wendeborn, and I'm representing Ursula today in this conference, and I'm a project engineer at Ramble. And at Ramble, we are consulting engineers, designers, and management consultants. And my team is specialized in asset management advisory for offshore wind structures. So, I hope you can bear with me today. In this presentation, I will give you an introduction to our approach to reducing the levelized cost of energy for offshore wind, using the example of the Romeo EU research project. And I hope to have some minutes left at the end of the presentation, so to directly address any feedback or questions. Otherwise, I'm also happy to stay a bit longer if necessary. But yeah, I'm optimistic that this will work out. Okay, first of all, who's Ramble? Ramble is an international engineering and design consultancy and provider of management consultancy to both the public and the private sector. Ramble was founded in 1945 in Denmark, and we employ 16,000 experts and work from more than 35 countries. Global presence with a particularly strong presence is in the Nordics, the UK, America, continental Europe, Middle East, and Asia Pacific. And our current annual turnover is approximately 1.8 million. And we are owned by the Ramble Founding. So that means that our activities are independent of any external or personal interests. We have no ownership or financial ties with contractors or suppliers. Our world-leading offshore wind consultancy department covers multidisciplinary services in all three project phases. That means we provide consultancy in the early planning phases of a project till the very last phase of decommissioning. So our consultancy is targeting the big picture of a project, and we base our services on the knowledge of 500 wind world-class energy experts from offices all around the world. We collected more than 30 years of experience in the onshore and offshore wind sector, and we are a global market leader in the detailed design of foundation structures for the offshore wind industry. We also have a large reference base within offshore wind substations, OSS, both in terms of quantities as well as design variants. Today, I want to focus on our digital-enabled asset management service, DEAM, where we combine the three disciplines of strategic asset management, digitalization, and domain knowledge. DEAM is built for asset owners to take informed, timely, and confident decisions about utilization, safety, compliance, and cost of their assets. Since more than 20 years, we are driving innovations for the offshore business, providing clients with the confidence to make good decisions. Always having the asset manager's needs in focus and making use of Industry 4.0 technologies to enable continuous and automated processes. So, coming to the topic of today, why is there a need to handle data as an asset? Meaning, why should an asset owner transition from traditional asset management strategies with corrective and calendar-based maintenance to a digital-enabled asset management strategy? To answer this question, I would like to present a few numbers. So first of all, there's a large variance in companies' annual operation and maintenance costs. It ranges from a bit more than 1% to 17% of total asset value. For lowest performing companies, this means there's a huge optimization potential. By introducing predictive maintenance, OPEX can be reduced for some clients between 10 to 40%. Lower downtime can be realized with up to 50% reduction, and future CapEx costs can be reduced between 3 to 5%. And the traditional way of doing maintenance, currently 65% is reactive, which is typically due to a lacking understanding of asset performance and condition. And digital-enabled asset management can potentially extend the lifetime of assets, improve safety measures, and optimize OPEX due to optimized maintenance strategies. So it's more than now like 4 years that my team of asset management advisory has started to define how the future of operation and maintenance in offshore wind will be shaped by more data coming in continuously. Since then, we have tested the ideas with a number of operators, built proof of concept and research environment, and also sharpened our understanding by project delivery. Today, I want to present the Romeo research project that has been a great journey for us to prove the concept for predictive maintenance and the two digital twin concept, and enabled us to put these technologies in commercial practice. Together with Ursula Smolka, I'm managing the work package 4 of Romeo, which is the development of structure condition monitoring strategies for offshore wind substructures. And I will now give you an introduction to our achievements. So, first of all, what is the Romeo project? Romeo is an initiative backed by the European Commission Horizon 2020 program, and it has a total project budget of 60 million euros, 10 of them financed by the European Commission, and roughly 2 financed by the Swiss government. The project, coordinated by Iberdrola Renewables, is being developed by a consortium of 12 companies and universities through the whole supply chain, including key technology partners such as turbine manufacturers Siemens Gamesa and Advin, utilities like Iberdrola and EDF, IT experts IBM, Indra, Uptime, foundation designers us, Ramble, component manufacturers Barman and La Lagoon, project consultants C expert Sabala, and the Strathclyde University. So the products developed in this project are tested in Iberdrola's wind farms, the Wikinger and East Anglia wind farm. Additional, EDF is making available Teesside wind farm for testing. The project started quite some time ago in June 2017 and will be completed in the upcoming summer 2022. So first of all, what are the objectives followed in this research project? On the right-hand side, you can see the result of one of our studies being conducted in Romeo, and we found out that the operation and maintenance phase contributes to around 30% of the levelized cost of energy of offshore wind farms. So Romeo's main objective is to develop models and tools allowing early fault detection on key components and the transition from corrective and calendar-based maintenance to condition-based maintenance. In the end, the Romeo project aims to reduce significantly offshore operation and maintenance costs, targeting a reduction by 8%. By introducing real-time intelligence in your maintenance strategy, expenditure can be reduced, performance of the asset increased, and the safety of the workforce being deployed offshore improved, because you can actively and agile react on the current situation and the current condition of your asset. In Romeo, Ramble is leading the work package to introduce real-time intelligence for the substructure condition monitoring. So following slides will focus on the substructures. And we set specific targets to be achieved. The reduction of the person hours required for annual inspections by 15% and the reduction of substructure inspection visits by 50%. The technology to improve safety, increase performance, and reduce expenditure has been developed within Romeo, and the impact assessment is now ongoing. So now how do we reach these targets? The project started with a failure mode and criticality analysis session for key major components, identifying critical failure modes to be further investigated in the project. A customized FMICA focuses on those mechanisms that take sufficient time before a failure materializes, hence allow sufficient time to react and plan for maintenance mobilization, failure prevention, or even mitigation. In Romeo, more than 60 failure modes have been investigated related to the substructures, and based on the criticality, purpose and objectives of the monitoring is defined. For the Wikinger project, which serves as a case study for our task in Romeo, almost half of the identified failure modes, a value-creating potential to make use of monitoring systems was identified. In our work package 4, we then developed and implemented advanced analytics and monitoring strategies targeting the previously specified monitoring objectives. For example, you can see here validation of the model, damages, and fatigue assessment. So, the solution for real-time intelligence being developed at Ramble is a true digital twin. That's a digital model continuously monitoring the structure by considering real-time information of the asset and its environmental condition. Maybe I can use my pointer. So that's a digital twin. Input to set up the simulation engine is typically the design reports. The simulation engine is then updated using information from inspection reports and measurements to decrease the discrepancies between the real structure and the simulation. In Romeo, we conducted an optimal sensor placement study to validate the condition monitoring system set up against the analysis goals identified in the risk assessment, and I will explain you this process in the following slides. So, having the updated simulation engine can be then used to generate relevant insights, such as the remaining lifetime, the identification of anomalies, and the evaluation of scenarios. And these insights are then condensed to specific recommendations, which forms the basis for decisions for example, inspection plan updates. Okay. As a first step, now we come to the optimal sensor placement study, as I have announced it. So as a first step to create a purposeful monitoring and analytics, a sensor pre-testing study is carried out, or should be carried out, to find out which sensors are needed to enable, first of all, the establishment of the digital twin, and also identify which failure modes can be monitored via virtual sensing. The goal in this study is to find the minimum amount of hardware and place them at the best accessible locations while enabling the extraction of the required mode shapes. Based on the monitoring strategy, accelerometers can be placed to exactly meet the demands for the digital twin. In this example, the Wikinger VTG is equipped with 5 accelerometers to extract the first 5 harmonics of the structure. Sensors are located on the transition piece and tower top. As a digital twin concept accompanies the structure during the entire life cycle, the sensors need to operate for at least 25 years. So, therefore, reliable sensors such as accelerometers should be preferred. As an example for identifying the feasibility for virtual sensing of a failure mode by a digital twin, I would like to show here the example of excessive scour formations. So, for scour detection, the natural frequency and mode shapes change when the global scour depth increases, as shown here in the diagrams. The colored lines correspond to mode 1 to 5. In this study, we could identify that the formation of excessive scour is clearly visible in the global eigenmodes, and therefore the condition monitoring system was designed to enable the extraction of the first 5 eigenmodes. So, having the optimal sensor placement in place, actually installed offshore, we then conducted the design validation and the reassessment of lifetime for 2 assets using that measurement data. And we did it once for the offshore substation and also for 1 wind turbine substation. For that purpose, we established the simulation engines using our in-house software RoseUp for the two structures, and then used the measurement data from the sensors collected offshore, to update the FE models. Having these simulation engines allowed us to evaluate the impact of the structural and environmental conditions on the behavior and the structural integrity of the asset. We recalculated the fatigue consumption with that enhanced simulation engine, and we were then able to indicate a significant potential for lifetime extension for both assets. That was obviously very exciting for us. Having the simulation engines established also allows to generate virtual measurement data to set up and validate methods for scenarios with a small likelihood to occur or to be detected in inspections. This is especially interesting for tracking anomalies which can cause catastrophic failures, such as the brace member loss subsea. Next to setting up to set up a digital twin, the main motivation followed actually in our work package is to introduce low-cost monitoring methods to improve the understanding of the offshore assets, lowering the cost of O&M, and ultimately exploit opportunities for lifetime extension. And low-cost monitoring in this context stands for the best value monitoring concept, using a few preferably robust and strategically placed sensors to indirectly monitor locations which are not equipped with sensors. So that's what we achieved with the optimal sensor placement. At the end, we were provided with continuous and short-term SCADA and condition monitoring system measurement data. And this data was then used to monitor the two identified critical failure mechanisms, fatigue and the selection of anomalies comprising structural anomalies and environmental conditions beyond expectations. And as you can see here in the overview of methods, the applicability of developed methods is dependent on the data availability. Having methods with different requirements for data enables the application of low-cost monitoring methods for varying quantity, but also quality of installed sensors. The insights being generated by the methods we developed are first of all of descriptive nature. The results give insight into the current condition of the structure. Next to the measurement data requirements, the methods also differentiate in their diagnosis and prognosis capabilities. That means the capability to identify causes of outcomes and predict future outcomes. I will now go a little bit more into the specific analysis goals and how we implement corresponding methods. Unfortunately, I can't see if any of you have some comments. Okay, seems all right.
Don't think there's any questions right now, Caroline. Sorry for calling you Ursula.
That's absolutely fine. It was quite a surprise that I'm replacing her, so no problem. So I'm not going into the specifics of our methods which we developed. So first of all, I will start with the monitoring of the fatigue consumption, which allows to make optimized decisions on the maintenance schedule. We demonstrated in Romeo the deterministic FE-based method, model decomposition and expansion, and you can see the results on the right-hand picture. The method estimates the stress rate at any component of the substructure using accelerometers on the tower and transition piece only, and the stresses are translated to fatigue damages to track the fatigue consumption of the components that are unfeasible to equip sensors. That's especially interesting for subsea locations or as displayed here in the splash zone. On the right-hand picture, you can see the estimated stress state at a component in the splash zone in comparison with the measured validation stress. And it was demonstrated that the model decomposition and expansion method gives satisfactory results for most elements of the substructure. In addition, we developed the fatigue damage regressor using a random forest algorithm. This machine learning method allows to track fatigue consumption of a component which was equipped for a short period with strain gauges, and for prediction it requires data only and also displayed satisfactory results. For fatigue monitoring, we were able to successfully verify our methods using strain measurement data collected offshore. To access information about the integrity of relevant structural components and relevant environmental conditions, we also developed status classification and normal behavior models. Those also belong to the field of machine learning, but they are coupled with physical models. The normal behavior models are limited to the identification of abnormal behavior. So you will just get an alarm, something went wrong, but you don't know what. And in contrast, status classification models trained with virtual measurement data can not only detect the presence of anomalies, but also indicate the category and location of anomaly. For example, as displayed here, it could differentiate between is it scour, is it a loss of a brace, and also which brace had a problem. The capability to identify anomalies was evaluated using virtual measurement data only, as we couldn't. Luckily, there were no severe damages at our case study wind farm to collect real measurement data to validate these methods. But yeah, these methods in general, validating with virtual measurement data, were also displaying satisfactory results. Our collaboration with other work packages and partners comprise the implementation of our developed algorithms in Internet of Things platform of IBM on the IBM Cloud, the visualization of results and the assessment of impacts on OPEX and CAPEX. And I will show you this, how it looks. So the monitoring results will be shown in an operation and maintenance information and management platform. It's called Harvest from Uptime, with integration of data, visualization for analysis, analytics, and automated advisory generation functionalities. And this platform also includes a link to our virtual reality model in Ramble, which we established for the whole wind farm, where monitoring results can be visualized for inspection planning and documentation. The impact assessment of the monitoring methods is done through an integrated impact assessment tool developed by the University of Strathclyde with 5 different modules, including CAPEX and OPEX, but also an environmental impact assessment module. So you have a direct insight in the impact of applying monitoring strategies. As a key message from this presentation, I would like to summarize the following. If you want to put yourself in the position of using real-time intelligence, make sure you collect the right data. That means the documentation, such as design, inspection, installation reports, should be specific. The sensor setup should be validated, targeting your analysis goals and chosen strategically. And also, it can be beneficial to think about equipping from beginning on the assets with a few more sensors to be able to validate your methods, as retrofitting is sometimes really costly and sometimes even not feasible. So if I got you interested in the digital twin technology, you might ask yourself, what is the optimal time to establish a digital twin? And here displayed are the expected benefits of structural digital twins applied at different life cycle phases. And in general, I can tell you there's not a bad time to establish a digital twin. So if the necessary data requirements are fulfilled, a digital twin can be established in the operational phase. And then the digital twin allows to analyze historical data, and the savings and return of investment start with establishing a risk-based maintenance strategy based on these findings. Optimally, the digital twin is already considered in the conception phase of a wind farm, so that the data requirements can be short and cost benefits maximized. So to summarize, before we start in maybe some discussions, I would like to highlight that collecting data only doesn't allow you to achieve operational excellence and your sustainability goals, because operational excellence comes from making confident decisions, and to make confident decisions, you need relevant insights, not data only. And for more information, please visit Romeo's website by using the upper QR code, which also includes training videos from various partners. And I'm also happy to share a white paper summarizing our lessons learned from digital-enabled asset management. And if you want to take full ownership of your wind farm assets to operationalize the data, and ultimately drive revenue, please use the second QR code to access this white paper. Yeah, thank you for listening.
Yeah, thank you, Carolina. And if anybody in the audience have questions, please post them in the discussion button that's up there to the right-hand side of the screen. Very interesting, very interesting. You said it in the beginning, but I didn't quite capture that the project has been going on for quite a long time.
Yes, exactly.
And I was curious also that the data, how fast is the data? Like scouring is a fairly slow phenomenon, right?
Yes, that's true. So obviously, like we also have some long-term studies. So the first data was collected in 2017. And now, like this continuous setup is implemented, and we have basically, I could just log in as IBM Cloud currently and just have a look at the data right away and run our analytics on it. And yeah, we see a few changes during those years, but they are not significant. That's for sure. So basically, we also have tasks which are analyzing the long-term effects on monitoring results. And these were mainly conducted with sensitivity studies, so that we checked different scenarios and see if these can be monitored.
So we have one question from the audience that says, most of the time operators try to avoid adding sensors to their assets. Does that approach undermine the efficiency of the studies conducted?
Mm-hmm. So first of all, it used to be common practice that wind farm owners are forced to put sensors on their wind turbines, and they just did it quite randomly. And we have actually shown in our analytics that there are really clear business cases for actually putting the sensors strategically. And for example, accelerometers are really cheap. So the motivation to install such sensor types is actually increasing by building up education of the wind farm owners, as they understand usually the big business case for them. But that's maybe true, for example, for strain gauges. They're quite expensive and also not that robust. So what we usually do is that we do not advise to equip all locations of a wind farm with strain gauges, because that would be really expensive and also difficult to maintain. But we make a strategically choice of which locations should be equipped with which sensors. So you basically can find the sweet spot between the appetite for investment and the actual expenses you would have to install the equipment. I hope that answers the question.
Yeah, I have an additional question. How many sensors are we talking about? Is it just a handful of accelerometers for each foundation, or how many sensors?
Yeah, so for the Wikinger setup, I can like in our optimal sensor placement, we defined a handful of accelerometers, some strain gauges, and you need a strain gauge ring. So basically, you always need 4 strain gauges, and including some temperature sensors and some inclinometers. But it's really just a handful of. Okay. Maybe 2 handfuls of sensors for the high equipped location. Like as you have seen maybe in the overview, we also develop methods which, for example, run on SCADA data only, which is available at any turbine. And then obviously you can gain insight in your structure's performance having a very minimalized sensor setup.
Excellent. Well, thank you very much, Carolina, and